First of all, what I am going to do, I'm going to present the syllabus that you are going to follow in this particular semester. Syllabus of Mathematics, whose code is BSM 101. Just look at the syllabus, and then I'm saying that what needs to be done. Okay. As you can see that this syllabus has actually 5 modules, and the first 2 modules are from calculus section. We have calculus the module 1 contains calculus section of integration. Module 2 contains the calculus section of differentiation. Some parts of this particular syllabus are probably known to you. So for example, so far as I know, probably you have learned Rolle's theorem in your school days, and you also know what is definite integral. Some parts are known to you, but some parts are not known to you. Okay. Look at the last 3 modules, module 3, module 4, module 5. Again, in module 3, some of the topics are known to you and some are not. Okay. And module 4 and module 5 is tremendously important for CSE section, CSE, because these 2 modules that you can see, vector spaces and or the module 4 and module 5 both are from vector spaces. This concept is very new, and it's very much, I can say that too much essential for learning artificial intelligence, machine learning, deep learning, quantum computing. My specialization is in quantum computing, and whenever you'll be in 7th semester, there is a course of quantum computing where this particular module 4-5 will be required to understand the subject. Okay, probably you have heard about quantum computers, but it is not I'm going to discuss right now. It is not the topic that I'm going to discuss right now, but I'm just saying that we shall concentrate mostly in these 2 topics. Okay, calculus is also required in machine learning mostly. So in machine learning, calculus is required, and not only the single variable calculus, multivariable calculus is required. Matrix is somewhat related to vector spaces, because although in the syllabus matrices are actually being taught, being represented separately, but matrix is a part of vector space. Okay, you will gradually understand. The most essential topic of this particular syllabus is these 2, 4 and 5, which is required in machine learning, in deep learning, in artificial intelligence, in quantum computing. Okay, so my point is that whenever you will be learning these 2 modules, 4 and 5, you shouldn't forget the things, because otherwise you will not be able to get the idea of your core topics from the CSE program. Okay, that is my suggestion. Okay, so this is the syllabus. Now in prerequisite class, what happens is that we have to discuss something which are not directly there in the syllabus, but are essential ingredient for learning the topics that are in the syllabus. That's why this prerequisite class is being taken. 2 prerequisite class has already been taken by the teacher in calculus section. I'll be covering some portions of algebra, especially from matrices and determinants, so that you can tackle the topics of module 4 and module 5 later on. As for example, if we need to know what vector space is, and if we need to know what matrix is actually, and if we need to know what is the difference between matrix and determinant, we need a concept which is called field. I don't know whether you have any idea about field or not, but that concept I'm going to give you right now. And after that, I'm going to talk about a few things about matrix and determinants. Okay. Now I'm moving on to a next page. This page is, as you can see, this page is a part of a book that I'm sharing with you right now. the name of the book will be told to you later on, but let's just concentrate on this definition, the definition of field. Okay. Now, first of all, let us try to find out what is written over here. I'm not, whenever that's the mathematics, in mathematics, whenever they talk about field, actually they do not mean the electric and magnetic field only. Field has a general concept under the purview of which everything comes and can be studied. And even your electric and magnetic field can be studied under the purview of this particular abstract mathematical structure, which is called field. Okay, so this algebraic structure, this is kind of algebraic structure that I'm going to explain to you right now. This algebraic structure is actually very important. The way you have learned mathematics in your school days, that is a symplectic approach. Now, since you are in in this undergraduate course, and you're going to do the higher mathematics and to apply them accordingly in a specific field. So you have to change your mindset, and you have to know how to do the analysis, because algebra is also a kind of analysis, and these type of topics like field and vector spaces, they play a very essential part. But I will say that this field, the structure field, is nothing new to you. Actually, you have worked on this. You have been working in this particular algebraic structure since your childhood. Only difference is that you didn't know this particular name. Okay. And with respect to my experience, while teaching school students, I have seen that in class 6 CBSE syllabus, a bit glimpse about the algebraic structure given in the book. You actually have to learn some properties related to integer sets, but I don't know whether schools pay much attention to this. School pay attention to XYZ, algebra, etc. But the actual ingredient, that is to know the structure in which these algebra actually play their respective roles. I don't know whether the school teachers pay attention to this or not. Probably they do so, but in some of the schools I have seen that they do not pay attention. They just skip that chapter. Now, what is field? Let's come to the main point. What is field? Field is an algebraic structure. Okay, it is an algebraic structure in which two operations, one is plus and one is dot, will be defined. This plus operation is usually called addition, and this dot operation is usually called multiplication. Okay, whenever this word addition and multiplication is written, they do not mean that this addition is only the addition of numbers, and this multiplication is not the multiplication of numbers only. By this, they mean it can be of any type of addition operation. Say, for example, if I talk about matrix, if I take two matrices like this is a matrix of order 2 by 2, and this is a matrix of order 2 by 2. When I add these two matrices, then what do? We add the terms individually like this. Okay, taking the elements from each of the matrices and adding the elements with their corresponding element of the other matrix. But this operation of addition that I have performed in case of matrix is a kind of addition, but it is not the addition of numbers. It is the addition of matrices. Okay. In this manner, there are many more examples that you will get to see gradually, where addition operation, different types of addition operations are there. And also, whenever I take a matrix like this, say for example, and if I multiply this particular matrix by a scalar quantity, then you know that this scalar quantity actually gets multiplied with each of the elements present in the matrix. So this is a matrix multiplication. This is a scalar multiplication of matrix. Okay, this is not the usual multiplication of numbers. So that's why I was saying that whenever they talk about plus as addition operation and dot as multiplication operation, they mean any addition operation, any multiplication operation with respect to the set under consideration. It is not just the addition and multiplication operation of numbers. And what else is written? So capital F is actually a set. Remember, this is a set on which these operations will be defined. Now, if I take two elements x, y from F, and if I add them as x plus y, and if I multiply them as x dot y, then this algebraic structure demands that this x plus y should belong to F, this x dot y should belong to F. This property is called closure property. Apart from this, with respect to this operation plus and dot, some other properties need to be satisfied. First of all, let us look at the property F1. What it is saying? It is saying that if you take any two numbers, A and B, then A plus B must be equal to B plus C. It's called commutativity of addition. And A dot B must be equal to B dot A. It is called commutativity of multiplication. These two properties need to be satisfied. Second property is F2, which demands that if I choose any three elements from the set F, then if I associate the two elements A, B with respect to addition, and then the outcome is associated with the third element in this manner, this is called association. The result is same as if I associate this B and C together, and the outcome is added with A. So in whatever direction you try to do it, the result is the ultimate result is same. This is called the associativity property of addition. And similarly, the associativity property of multiplication is also there. It's the second property that the field structure demands. Also, we need to find a kind of element. Okay, the element is written as 0. This 0 is not always, remember, this 0 is not always the number 0 I'm talking about. Okay, so this 0 is such an element that which when added to any element of the set F gives back the element and doesn't change it. So 0 plus A must be equal to A. And similarly, we need to find an element 1 in F, which when multiplied to any other element of F gives back the element. So that is written as 1 into A, which is A. Okay, and this particular element 0 is called the additive identity. Okay, and this particular element 1 is called the multiplicative identity. So this will be called additive identity, and this is called multiplicative identity. We need to find these elements in the set capital F. Once this is done, then we go to F4, and in F4, for each element A in F, we need to find an element C. For A, we need to find an element C, so that A plus C gives you the additive identity. And for each non-zero element, just look at this point, for each non-zero element B, we need to find an element D, so that B into D gives you 1. Okay, this is what the property F4 demands. And lastly, we need to have a property which combines. Now you just look at the properties F1, F2, F3, F4. Separately, these properties have been written: A plus B, B plus A with respect to addition, A dot B, B dot A with respect to multiplication. In F2, we have A plus B plus C is equal to A plus B plus C with respect to addition. And A dot B dot C is equal to A dot B dot C with respect to multiplication. Then in F3, we have 0 plus A is equal to A. 1 dot A is equal to A. In F4, we have A plus C equal to 0 and B dot D equals to 1. In each of these cases, plus is separated, dot is separated. Now in F5, what they are doing? They are combining this dot and plus operation together. This property is called a distributive property. But why is it called distributed property? Because this multiplication operation is being distributed to each of the elements present inside the bracket. So I am combining the elements A and B together with dot. This outcome is being combined with the product A dot C with the operation plus. So dot is actually operating on each of these elements. So A dot B plus C is equal to A dot B plus A dot C. This is called the distributive property. Each of these properties that I have mentioned, I think these properties are not actually unknown to you. These properties are very much known to you. But only difference is I'm again saying that you didn't know that we have a kind of structure in which we are actually performing our mathematical operations. Okay, let's do some board work. Otherwise, the thing will not be understood by you. Okay. Whenever I talk about some algebraic structure, we actually call them space. In this space, we are actually allowed to do some kind of operations. If we move out of the space, we shall not be able to play the mathematical operations. Okay. So field is a kind of algebraic structure, is a kind of space in which we are allowed to do some kind of operations. So what have we learned from our previous slide is that we need to have a set F. On this set, we need to define an operation plus, an operation dot, and this triplet is actually called field if certain properties are satisfied. So we have come across all the properties, and now I'm going to show you some examples where we have certain sets which are not filled, and we can have certain sets, those are fields. So I'm starting one by one. Now you will find it interesting, and you will be able to understand actually what I was talking about. Suppose I'm considering F to be the set of natural number. Remember that if all the properties that were shown to you earlier, if all these properties are satisfied, then the structure is filled. Then the structure is filled. You don't have to take any note right now because I will send you the note later on. If all the properties are satisfied, then the structure is filled. But if at least one property is violated, the structure is not filled. The structure is not filled. So for the violation, you have to show that at least one property is not being satisfied. Okay, so let's try to find out. Okay, for your understanding, I am quickly writing all the properties over here so that you can easily refer to these properties whenever it is required. The first property was F1, which was like this: A plus B must be equal to B plus A, and A dot B must be equal to B dot A. F2 was A plus B plus C should be equal to A plus B plus C, and A dot B dot C must be equal to A dot B dot C. F3 is we must get some element called 0, additive identity, so that this happens, or you can write it in this following manner. Doesn't matter because it is commutative. And similarly, we need to get an element 1 so that this happens, or you can write it in the following manner. F4, that for each element A, we need to get an element A prime so that their outcome is 0. For each element A, if for each non-zero element A, we need to get an element A double prime so that the outcome is 1. A dot A double prime is 1. And the last property, F5, is the distributive property, which combines dot operation with plus operation, which is equal to A dot B plus A dot C. Now, suppose we have been thrown in this particular mathematical structure, and in this structure, we need to perform this operation. We are supposed to perform this operation carefully. Then we have to be very careful about the fact that the set which I'm dealing with, its elements need to satisfy each and every property. If at least one of these properties are violated, then we'll say that, okay, this is not filled. The structure is not at all filled. So to show this, I have considered the example where my set is the set of natural numbers. Now you see what happens is that, and moreover, before we check the properties, the closure property is also very important. Closure property demands that if you choose two elements from the field, then we must get X plus Y belonging to the set itself. And not only this, if we choose two elements X, Y from the field, demands that their product X dot Y needs to be in the field. So this property, after checking the closure property, we need to check individually whether each of these properties are satisfied or not. For natural number, if you consider any two natural numbers, their sum is also a natural number, and their product is also a natural number. So obviously the closure property holds for a set of natural numbers. Okay. If you consider any two natural numbers, and if you add them, then commutativity, A plus B equal to B plus A, they actually hold. Commutativity with respect to multiplication is also satisfied. So we do not have any problem with F1 in case of the natural number. Similarly, it is easy to verify that you can associate the natural numbers according to these rules of association with respect to addition and multiplication. So natural number is associative with respect to addition operation and multiplication operation. But whenever you come to F3, you will see that in the set of natural number, as you know, the natural number set starts from 1, 2, 3, and goes on up to infinity. No zero, no such element is present, which when added to natural number gives back the natural number. So this property is actually getting violated over here. We do not find any such number in the set of natural number. Okay, and therefore natural number set n is not a field. Whenever you are going to check these properties, the way I have presented all the properties here, they have to be checked in this sequential manner. It is not like that suddenly you go to F4 and checking F5, and then you are coming to check the closure property and then F1 and then F2, not like this. You have to go in a sequential manner. Okay. First, you need to check F1, then you need to check F2. In my set of natural numbers, these were satisfied. There were no problem with this. But when I wanted to check F3, I couldn't find any natural number such as 0, because 0 is not a natural number at all. We couldn't find any natural number which, when added to any other natural number, gives back the natural number. So we'll automatically say that natural number set is not a field. We don't have to check other properties, because I said if at least one property is violated, the structure is not a field. Okay. So mathematicians thought, okay, if this is the scenario, then let us consider a non-negative whole numbers like this. This set is called the set of non-negative whole numbers. Okay. So if I include 0 now in the set, you will see that F1 will be satisfied for both addition operation and multiplication operation. F2 is satisfied for both addition operation and multiplication operation. Now F3 is getting satisfied. No problem with this, because we have 0 now, and this gives me that any other element when added with 0 gives the element in return, and 1 was already present. So any element multiplicative identity 1 is already present, was present in the natural number set. So that was being satisfied already in the previous case also. But up to F3, now we do not have any problem. Up to F3, we do not have any problem. But when we go to F4, again, we are faced with a problem, because F4 demands that to every element A, first of all, let's talk about the additive case, I mean the addition case. To every element A, there must exist an element A prime, so that when they are added, the result is 0. In this particular set, no such element is present. We cannot find an element which, when added to another element, gives you 0. So this is not being satisfied. And also, if you want to check this one, consider any non-zero element, that means starting from 1 to 3, etc. And you will find that for this, you will not be able to find its reciprocal in the set of non-negative whole numbers, so that this is satisfied. Rather, you don't have to check it, because the first case, A plus A prime is equal to 0, is not getting satisfied. So this is the problem that we are facing right now with the set of non-negative whole numbers, and therefore non-negative whole numbers W is not a field. It's not a field. So anyways, the mathematicians thought that, okay, probably we have to redesign our set of numbers in such a way that so that we can get a field out of it. So then what they did is that they considered Z, where they included all the non-negative whole numbers going up to infinity, and their negative counterparts also. And you know that this particular set is called the set of integers. Z stands for Zellin. Now you see that now for this particular set, F1 is satisfied for both addition and multiplication. F2 is satisfied for both addition and multiplication. F3 is satisfied for both addition and multiplication, because additive identity is present. multiplicative identity is also present. And now if I go to F4, we find that to each element, say for 1, we have -1. So if I add 1 and -1, the resultant is 0. 2 is associated with -2. 3 is associated with -3. So every element has got its additive inverse. 0's additive inverse is itself. 0 plus 0 equal to 0. So now it is getting satisfied. No problem with this. But again, if I want to check this with respect to multiplicative identity, we see that for no element, no non-zero element in Z, reciprocal exists. So this is getting violated now. Multiplicative identity is absent, and therefore Z is not a field. Z is not a field. So in our school days, we learned about set of natural number. We worked on that, which is not a field. We learned about non-negative whole numbers. It is not a field. We designed set of integers. It is not a field. And then mathematicians thought that, okay, probably we are not yet done. We have to do something else with our set of natural numbers. And thus they designed the set of rational numbers. And you know that this set of rational numbers with the help of set builder form can be written in the following way. It contains all the numbers of the form P and P by Q, such that P, Q are relatively prime to one another and Q not equal to 0. The common multiple of P and Q is 1. Okay. So common divisor of P and Q is 1. So it is a set of rational numbers. And when they talk about rational numbers, if you now try to find out whether the properties F1, F2, F3, F4, and F5 are being satisfied or not, you will see that for each and every rational number present in Q, F1 is satisfied, F2 is satisfied, F3 is satisfied, F4 is satisfied, F5 is satisfied. Why? Because now 2 has got its inverse half, so that this is 1. 3 has got its inverse 1/3, so that it is 1. 2/3 has got its inverse, which is 3 by 2, so that it is 1. 0 we shall not consider because we are only talking about the inverse, multiplicative inverse of non-zero element. My class is going to end right now. So I'm stopping over here, and we shall continue in the next session. You join by clicking the link once again.